Hi, welcome to a session on VLSI Design Automation. I'm Dr. Roji, and in this session, I'll explain about the different aspects of switch level simulation, the parameters involved in it, and how this varies from circuit to circuit. In this lecture, we'll see some basic aspects of the switch level simulation. Every signal has a pair associated with it. The parameters in the pair are the strength and the level. The strength is directly related with the impedance associated with it, and V is the level which is associated with the voltage. The possible values of the voltages are 0, 1 and X. Bryant has proposed a model of the strength values. There are W distinct strength values given by Bryant, which are 1, 2, up to K up to W, right? And we will see what are the strength values of some elements. Nets. Nets can be either input nets or the storage nets. The input net is the one which is connected to either VDD or VSS. So the strength of the input net is the maximum, which is S is equal to W, right? The storage net is related to or is taking the input value or the output value. The storage net has a value of 1 less than or equal to S less than or equal to K, right? The next one is the transistor. The transistor is given with a strength. So whatever signal which passes through the transistor will be reduced to the maximum strength that which can be accommodated by the transistor. So if you are passing a signal with a strength greater than S through a transistor, the strength of the signal will also reduce to S. Okay, so this one, the transistor reduces the value, it reduces the strength of all the signals which pass through it. Okay, we'll see the working of the strength model by taking some classic examples. The first example is the static CMOS. So in the static CMOS, we have a PMOS transistor network and an NMOS transistor network. The static CMOS is called so because the circuit operation is independent of any clocking strategy, right? So when the input voltage is 1, the NMOS network is on, right? The output voltage is pulled low. This is my output. The output voltage is pulled low and the output voltage becomes 0. Vout is equal to 0. When the input voltage becomes 0, the PMOS transistor network is on and the output voltage is pulled high. So the output voltage becomes 1. This is the basic of any static CMOS network. The same block can be represented as a circuit as shown here. So we can now substitute the values of the nets. Here I have a net, input net, which is connected to VDD and another input net which is connected to ground. So I'll call this input net as N1 and it will have a value of 5. This also will have a value of 5. Whereas we have a input net, a storage net here and a storage net here. The storage net, I'll call them as N2. N2 is equal to 1. And this one also we can give it as N2 is equal to 1, right? So next we'll see what should be the strengths of the transistor. The strengths of the transistor, I'll call them as, for simplicity, I'll call them as transistor A and transistor B. The transistors A and B, the strengths of these transistors, they do not have a vital role to play. When you go deep into the working of the static CMOS, you will understand that even they have a role. But here, since we are at the basic level, we'll assume that the strengths can be the same. So I'll take the strength of this transistor as 3 and the strength of the transistor B as 3. Okay. So, as I said, let the input voltage V in be 1. V in is 1. So now my NMOS will turn on. When the NMOS turns on, current will flow through this path, right, through the transistor which has a strength of 3, and my output will be what? 3, 0. Okay. When my input voltage is 0, what happens? The PMOS turns on, current flows through the PMOS. The PMOS transistor also has a strength of 3, but output voltage becomes 1. Okay, this is the operation of the strength model in a static CMOS. We'll see one more circuit here, right? This is the NAND implementation using static CMOS. As we all know, in a NAND implementation, the two transistors in the pull down should be in series and the two transistors should be in parallel in the pull up, right? So the transistors, all the transistors are given a strength of 3 here and 3 there, right? And NO of 5 is my input net. It's given a strength of 5. N3 of 5 is the input net which is connected to VSS. It also has a strength of 5. N1 is a storage net and N2 is a storage net. Each have been given a strength of 1. Right? So I hope this is clear. We'll see the next one. We'll see the strength model by our next example, the depletion load NMOS inverter. In the case of the static CMOS, we had a pull up and a pull down, and the output will be drawn either towards the pull up or towards the pull down. In the case of depletion load NMOS inverter, as you can see here, the pull up is a depletion load, right? The pull up is a depletion load, and the pull down is a normal enhancement transistor, right? So I'll call this pull up as A and the pull down as B. In the pull up A, the gauge is shorter to the source, so the depletion load is always on, because VGS, even when VGS is equal to 0, the depletion load can function. So this depletion load is always on. Right, now I'll see the different conditions one by one. I'll take the first case, right? The first case, let V in be equal to 0. When V in is 0, the transistor B is off, right? And the transistor A is always on. Okay, so what will happen now? The output voltage, output node will be pulled towards the VDD. So output voltage will be equal to 1. Right? I'll take the second case, case 2, and I'll assume Vin is equal to 1. Now what will happen? My transistor B turns on, A is already on, A is always on. So now there will be a competition between the transistors A and B. V out will be pulled up towards VDD, and it will also be pulled down towards ground. So what can I do now? This is an inverter circuit, am I right? So when Vin is equal to 1, what do I want? What do we want? We want the output voltage to be 0. This is what we expect. How can that be made to happen? So only the pull down network should be on. But pull up is also on. What do? I will increase the resistance of the pull up network to be more than the resistance of the pull down network, so that conduction occurs only through the pull down when V input is equal to 1. So this type of circuits is called the ratioed logic. There should be a ratio between the pull up network and the pull down network, right? So in this case, this is happening. So in terms of strength, what can I say? I can decrease the strength of the pull-up network to be lower than the strength of the pull-down network, right? So this is the, in terms of strength, I can write it as strength of pull-up network, right, should be less than strength of pull-down network, right? When I go back to my circuit, I can say that this strength, the strength of the PMOS, I'll make it as 3, and the strength of the NMOS, I'll make it as 4. It is to satisfy the ratio. Is that clear? And this one is the input net. We don't have any problem with it. I'll give it a strength of 5. And this one is again a storage network. I'll give it a strength of 5. Okay. And this one, I'll call it as N1. The strength will be 1 as before. Okay. So now I have constructed an NAND gate using the same depletion node NMOS. So this is a NAND gate which has been constructed using the depletion load NMOS inverter. Okay. So the operation need not be explained again. We'll see what should be the strengths. Okay. So as we know, the strength of the pull-up network should be less. So the strength of the pull-up network will be 3 here, and this one will be 4. This will be 4. The strength of the input net is N1 of it is 5. The strength of the pull down, strength of the VSS is 5 again, right? And then this in storage net, I'll give it a weight of 1. This one I'll give it a strength of 1. So this is how I adjust the strengths. So now we'll take the same analysis here, but in a different light. So case 1, let this is A. Let A is equal to B is equal to 0. So what's happening here? The whole of pull down network is off. Okay. So what will be my output voltage? Output voltage will be, output is now pulled up towards VDD. Is that clear? So output voltage will be 1. How do I write this? It is 3, 1. Right? Case 2. Case 2. This is a NAND gate. I want you to remember. So the NAND gate, let A is equal to B is equal to 1. For all the other cases, output will be the same as the previous case. Right? Let A is equal to B is equal to 1. So what will happen? Pull down network is on. Pull up network is also off, but the conduction is reduced because the strength of the pull up network is 3 now. Right? So what will be the output current, output voltage? Now the output voltage is pull towards ground. So the output voltage will be output voltage will be 4, 0. Right? It is pulled towards 0 through the transistors whose strength is 4. Right? We'll come to the next one, the domino logic CMOS. Here again, we have almost the same structure, but with a difference. We have a clock phi which is connected to the pull up and to the pull down. Right? So we should see if it is ratioed. Is it ratioed? It is not ratioed because when phi is equal to 0, what happens? The pull up network is on. When phi, and what will happen to the pull down network? Pull down network will be off since the same phi is connected here, right? So the pull down network will be off irrespective of what are the values of A and B. The next one, so this is case 1. The case 2 can be case 2, phi is equal to 1. When phi is equal to 1, the pull up network is off and the pull down network will be on, or it will be conditionally on. What do you mean by conditionally on? It will be on depending on the values of, it will be on depending on the values of A and B. Am I right? It will be on depending on the values of A and B. So there is no problem. The circuit is completely not ratioed. The circuit is completely not ratioed, but our worry is what should be the strengths. Since it is not ratioed, we can have the same strength for all the transistors. For the pull up it is 3, for the pull down also it is 3, here also it is 3. But now we have a problem in this particular circuit. This circuit problem is called charge sharing. For this, assume V out is charged. V out is charged to our CDD. It is storing a value of 1. Okay. And A is 1, B is 0. So what might happen? Charge sharing can happen through the first transistor. In order to avoid that, we make the strength of the node N1 as 2 and the strength of this this net as 1. Is that clear? So this is the only thing which has to be made here. So when the transistor is pull up network is on, output will be 3, 1, and when the pull down network is on, the output will be 2, 0. That brings us to the session of this particular circuit with more interesting sections. I'll meet you in the coming classes. Thank you.